There is a kind of question that sounds innocent until you ask it carefully. What existed before time began? At first, it seems like the most natural question in the world. Every event has a cause. Every cause has an earlier cause. Every room has a hallway before it, every hallway another door, and behind that door, one more room. Human beings are creatures of sequence. We trust the logic of earlier and later the way fish trust water. So when we hear that the universe had a beginning, we do what the mind has always done. We look behind it. What came before the Big Bang? What was there before the universe? What was happening before time started? And it is right there, in that last sentence, that the ground begins to give way. Because physics does not merely struggle to answer that question. In some of its deepest forms, it questions the grammar of the question itself. Not because science has become evasive. Not because cosmologists are hiding behind equations. But because the universe may be stranger than the language we use to ask about it. The beginning may not be a moment inside time. It may be the place where time becomes possible. We may be asking for a before in a region where before has no stable meaning. The oldest human instinct is to demand an earlier room behind every door, while physics may be telling us the hallway itself begins here. That is the terrifying truth. Not that we have found some monster behind the beginning. Not that there is definitely nothing there. Not that science has already solved the ultimate origin. The truth is worse for intuition and better for mystery. The universe may not fit the temporal habits of the mind that evolved inside it. Tonight, we are going to move into one of the most dangerous questions in cosmology. Dangerous not because it leads to superstition, though it often does. Dangerous because it leads to a frontier where ordinary words, before, after, cause, beginning, nothing, begin to fail in public. We will separate what is established from what is interpreted. What mainstream cosmology strongly supports from what speculative quantum gravity merely suggests. What physics actually says from what headlines and metaphysics like to add. And by the end, we may not know what existed before time began. But we will know something more unsettling. We will know why the universe may not owe us a before at all. There are questions that science can answer by building a better instrument. What is inside the atom? What is the spectrum of that distant star? How fast is the universe expanding? What is the mass of that black hole? Then there are questions that force science to examine its own language before it examines reality. What existed before time began, is one of those. The danger in this question is not that it is foolish. It is that it feels so reasonable. The question seems to come preloaded with common sense. If the universe began, something must have preceded it. If time started, there must have been a prior condition in which time was waiting to start. If there was once nothing, why is there something now? Each step feels natural because our minds are built from everyday causality. In ordinary life, beginnings happen inside a larger backdrop. A song begins inside time. A city begins inside history. A life begins inside a universe already underway. But cosmology is not about local beginnings inside a larger stage. It is about the stage itself. And that changes everything. Modern cosmology does not describe the Big Bang as an explosion into pre-existing empty space. That image is one of the most persistent and misleading myths in all of science. The Big Bang, in mainstream physics, refers to the hot, dense early state of the universe and the subsequent expansion of spacetime itself. Space was not a container waiting to be filled. Time was not a silent clock already ticking behind the curtains. In the classical picture, spacetime is part of the thing whose history we are describing. That means the question, what happened before, becomes slippery in a very specific way. If time is part of the universe's structure, then asking what happened before time may be like asking what is north of the North Pole. The problem may not be hidden data. It may be broken coordinates. But the story does not end there. Because modern physics is not content with easy dismissals. General relativity predicts singular behavior if we extrapolate backward far enough. Quantum theory tells us classical pictures become unreliable under extreme conditions. Quantum cosmology, inflation, no-boundary models, bounce scenarios, loop quantum cosmology, eternal inflation, and other frontier frameworks all reopen the origin problem in different ways. Some suggest the classical beginning is not the ultimate beginning. Some suggest time changes character near the origin. Some suggest our universe emerged from a prior phase. Some suggest the concept of before must be redefined rather than rejected. This is why the question is dangerous. It lives at the intersection of three different things people constantly confuse. First, established science. Second, legitimate interpretation. Third, speculative extrapolation. If we fail to distinguish those, then origin questions become a carnival. Mystics call it proof of mystery. Popularizers call it proof of impossible paradox. Skeptics call it proof the question is meaningless. But none of those positions is fully satisfying. The truth is harsher and more precise. Some versions of the question are indeed malformed. Some versions remain physically fertile. And some of our deepest theories seem to be telling us that reality near the beginning does not resemble ordinary temporal intuition at all. That is where we are headed. We are going to begin not with equations, but with the human instinct that makes this question almost impossible to resist. Because long before there was cosmology, there was a psychological hunger that still drives the whole problem. The hunger for an earlier cause. Long before physics, there was memory. And long before memory, there was sequence. Animal minds survive by tracking order. First the rustle, then the predator. First the fire, then the pain. First the sunrise, then the warmth. Minds that ignore sequence do not last. Cause and effect are not abstract philosophical luxuries at the biological level. They are survival tools. So the human brain became a machine for asking what happened first, what caused what followed, and what hidden event lies behind the visible one. That is why the question of origins grips us so deeply. It is not merely scientific curiosity. It is the oldest structure of explanation we possess. A child asks where rain comes from. Then where clouds come from. Then where the sky came from. Then where everything came from. The question extends itself with ruthless innocence. Every answer that ends the chain feels emotionally suspicious. The mind wants one more room behind the door. This instinct is so strong that we often mistake it for logical necessity. If something exists, we say, then there must have been something before it. If a story begins, we assume it begins in a larger story. If the universe has a first moment, surely there must be an earlier condition from which that moment emerged. But that confidence may be a projection of local life onto global reality. The human brain evolved in a world where beginnings happen against backgrounds. A tree grows inside an already existing forest. A storm begins in an already existing atmosphere. A civilization begins on an already existing planet. We never encounter absolute beginnings in ordinary life. We encounter transitions. So we internalize a rule: every beginning is really a rearrangement of something earlier. Cosmology may be the first place where that rule stops being obviously valid. This does not mean the instinct is worthless. Quite the opposite. It is one of the reasons cosmology exists. We ask what came before because explanation, in almost every other domain, advances by looking behind the present state to prior conditions. Stellar evolution explains stars by earlier gas clouds. Planet formation explains worlds by earlier disks. Biological evolution explains organisms by earlier lineages. Of course, we try the same move on the universe itself. The trouble is that the universe is not an object inside a larger observational frame. It is the total arena within which all ordinary frames exist. The moment you ask what came before the universe, you risk importing assumptions from local phenomena into the one case that may not permit them. Still, the instinct persists because it is emotionally inseparable from causality. To ask, what came before, is often really to ask, what made this happen? We are not just curious about sequence. We are hungry for explanation. If the universe exists, why? If it began, why then? If time emerged, what brought it forth? This hunger is so strong that even when physicists warn that the question may be malformed, many people hear that as evasion. It sounds like a refusal to explain. But often it is the opposite. Sometimes the deepest explanation requires showing why a familiar question is built on the wrong coordinates. Think of asking what is east of the eastmost point on a globe. The question feels spatially structured, but its structure is flawed. The answer is not a secret location. The answer is that the geometry of the surface defeats the implied extension. That does not mean geography failed. It means the language of the question overreached. The possibility facing cosmology is similar. We may be demanding an earlier room behind every door because that is how primate explanation works. Physics may be telling us that at the beginning of the universe, the hallway itself runs out, or changes character so radically that, behind the door, is no longer a stable picture. This is part of what makes origin questions so haunting. They are not just about the universe. They are about the limits of the cognitive habits with which we confront the universe. We want the origin to obey the same grammar as every other event in our lives. It may not. And yet the instinct remains powerful enough that we cannot dismiss it casually. If we are going to say the question, what existed before time, might be partly malformed, we owe ourselves a careful account of what the Big Bang actually was. Because much of the confusion begins there. The phrase, Big Bang, may be one of the most successful scientific names ever coined. It may also be one of the most misleading. To many people, the name suggests an explosion. A blast of matter into empty space. A detonation at a point, followed by debris flying outward into a larger void. This picture is intuitive. It is also wrong in almost every important way. In mainstream cosmology, the Big Bang is not an explosion in pre-existing space. It is the hot, dense early state of the universe, together with the expansion of spacetime itself. That difference is not cosmetic. It changes the entire emotional and conceptual structure of the origin problem. If the Big Bang were an explosion in an already existing container, then asking what existed outside that container or what happened just before the blast would feel straightforward. But if the Big Bang refers to the early behavior of spacetime itself, then the old picture of an event happening inside a larger arena no longer applies. The standard cosmological model, built on general relativity and supported by observation, tells us that the universe has been expanding from an earlier, denser, hotter phase. Evidence for this includes the observed recession of galaxies, the cosmic microwave background, and the primordial abundances of light elements. Together these form one of the strongest frameworks in all of science. None of that says the universe began from nothing, in the casual sense. None of it says there was definitely a single point-like explosion. None of it says we currently understand the absolute origin. What it says is that as we trace the universe backward in time using classical general relativity, density and temperature rise, and the scale factor of the universe shrinks. Eventually, classical physics drives us toward an apparent singular origin, a regime where our equations signal their own failure or incompleteness. This matters enormously. The Big Bang model is not the claim that we know everything about the first instant. It is the claim that the observable universe emerged from a hot, dense early phase whose fingerprints remain visible today. That distinction is often lost in public discourse. People hear Big Bang and imagine science claiming to have watched the universe pop into existence. What physics actually gives us is subtler and more disciplined. It gives us a robust account of early cosmic evolution back to extremely early conditions, then warns us that near the putative beginning classical description becomes unreliable. This is where the real mystery begins, not where it ends. Because once the Big Bang is understood correctly, the origin problem becomes stranger than the explosion myth ever allowed. We are not asking what caused matter to fly into emptiness. We are asking about the status of spacetime, causality, and temporal order at the edge of classical cosmological description. And that immediately raises another issue. Why do we keep speaking as if space and time are background stages waiting for events to occur upon them? General relativity teaches something more unsettling. Space and time are not passive containers. They are dynamical, physical, interwoven aspects of the universe's structure. The arena is in the play. And if the arena itself has a history, then the question of before becomes far more dangerous than it first appeared. In ordinary life, space feels like the room and time feels like the clock. Space is where things are. Time is when things happen. The room could, in principle, remain even if the furniture changes. The clock could, in principle, keep ticking even if no one is watching. This intuition is useful at human scale. It is also one of the first casualties of modern physics. Einstein's relativity did not merely revise gravity. It restructured the stage on which reality appears. Space and time are not independent backdrops. They are fused into spacetime, and spacetime is not inert. It bends, stretches, and evolves in response to energy and matter. Gravity is not simply a force acting across a pre-existing arena. It is geometry becoming dynamical. This is one of the deepest reasons the origin question becomes so unstable. If space and time are part of the physical structure of the universe, then asking what happened before the universe may be less like asking what happened before a local event and more like asking what happened before the stage itself had the properties that make events locatable. In classical cosmology, when we say the universe expands, we do not mean galaxies are flying outward into external emptiness from a central point. We mean that the spatial relations described by the metric of spacetime are changing. Space itself is stretching. Distances between sufficiently distant galaxies increase not because they are sprinting through a static cosmic hall, but because the hall's geometry evolves. The same is true, in a more subtle sense, of time. Time in relativity is not a universal cosmic river flowing identically for all observers. Different observers can slice spacetime differently. Simultaneity is not absolute. There is no privileged, universal, now built into the deep structure of relativistic physics. Already that should make us cautious. If even within the universe there is no single master clock in the naive sense, why should we assume that before the universe is a stable phrase? This is not mere philosophical fussiness. It is a direct consequence of the way modern physics describes reality. Time is not a divine metronome hovering above the cosmos. It is part of the relational structure the cosmos instantiates. Once you understand this, the beginning problem stops looking like an ordinary event at the first page of a book. It starts looking like a place where the very grammar of pages may be under revision. There is a recurring temptation, especially in popular language, to smuggle Newtonian habits back into cosmology. People say, okay, maybe the universe began, but surely time was already there waiting. Yet in the relativistic picture, that is no longer an innocent assumption. To imagine time is already there in the ordinary sense is to reintroduce a background structure the theory has taught us to be suspicious of. Still, relativity alone does not settle everything. It gives us a classical framework. And when that classical framework is pushed toward the earliest conceivable conditions, it leads to one of the most famous and misunderstood ideas in cosmology. The singularity. A word that sounds like final certainty and actually means something much more troubling. If you run the equations of classical general relativity backward, the expanding universe appears to approach a singular state. Density grows. Temperature rises. Curvature intensifies. Scale shrinks. Eventually the mathematics points toward a singularity, a place where quantities blow up and the ordinary predictive language of the theory ceases to behave well. This has led many people to imagine the beginning of the universe as a literal infinitesimal point of infinite density from which everything burst forth. That image is dramatic. It is also an overinterpretation of what the mathematics is telling us. A singularity in physics is not usually a triumphant declaration that we have located reality's final brick. More often it is a warning sign that the theory being used has reached a regime where it no longer speaks reliably. The infinities do not necessarily prove that nature contains actual physical infinities in the simple way the equations suggest. They often indicate that our description is incomplete. This is true in cosmology just as it is in black hole physics. Singularity theorems show that under broad classical conditions, geodesics cannot be extended indefinitely into the past or into collapsed regions. They do not, by themselves, tell us the ultimate microscopic structure of reality at those boundaries. That is why singularities are both important and easy to misuse. Important because they mark the place where ordinary classical description reaches its limit. Easy to misuse because people mistake that limit for a completed metaphysical picture. So what do singularities tell us about before time? They tell us, first, that classical general relativity does not provide a smooth, trustworthy story all the way to a clean, intuitive temporal origin. If you push the theory to the earliest conceivable regime, the theory itself signals distress. That means any confident statement about what happened at the first instant, let alone before it, already exceeds the strict authority of classical cosmology. This is not a defect of science. It is one of science's greatest strengths. A theory that knows where it fails is more trustworthy than a theory that pretends omniscience. The singularity is the universe, or rather our mathematics of the universe, telling us that deeper physics is required. And what deeper physics is that likely to involve? Quantum theory. The same quantum principles that dominate atoms, fields, and the microstructure of matter are expected to become decisive when spacetime itself is pushed to extreme conditions. Near the putative beginning, classical spacetime may no longer be the right language. Geometry may fluctuate. Time may cease to behave as an ordinary parameter. The distinction between history and possibility may become blurred in ways ordinary intuition cannot easily represent. This is why the origin problem is not merely a matter of extrapolating one more second backward. At some point, one more second backward may stop being a meaningful operation. Here the emotional danger grows sharper. People often imagine science as gradually illuminating the dark with the same sort of light. But at the beginning, the kind of light may have to change. The question is not just hidden facts inside familiar coordinates. It may be the breakdown of the coordinates themselves. That is what singularities really threaten, not just ignorance, but familiar intelligibility. And once you accept that, the phrase, "before time began," can no longer be treated casually. If time as ordinarily understood is part of the classical structure that fails near the origin, then before may itself become unstable. So now we arrive at one of the most unsettling questions in the whole documentary. If time begins here, what happens to before? The simplest answer is also the one most people hate. If time begins here, then before may not apply. This is often compared to asking what lies north of the North Pole. The analogy is imperfect but useful. North is a directional relation defined on a surface. At the pole, that relation runs out. Not because something mysterious blocks the way, but because the geometry of the system does not support the extension the question demands. Likewise, if physical time has a boundary or a beginning in a meaningful sense, then asking what happened before may involve a misuse of temporal language. Before is a relation inside time. It presupposes a framework of earlier and later. If the framework itself is what begins, then the relation may not survive the edge. This is the point at which many people feel science is becoming evasive. It sounds like semantic trickery. But it is not. It is an attempt to take the structure of the theory seriously rather than imposing the habits of everyday reasoning where they no longer fit. Imagine trying to define yesterday in a universe where time had not yet become a meaningful dimension. The word fails not because yesterday is being hidden from you, but because yesterday is only meaningful inside a temporal order already in place. That may be what origin cosmology is telling us. The beginning may not be a moment inside time but the place where time becomes possible. If that is right, then the phrase, "before time began," is not merely unanswered. It is grammatically unstable at the physical level. The mind asks for an earlier room behind the first door, and physics replies that the hallway itself may begin there. But notice something important. This does not automatically prove there was nothing prior, in every conceivable sense. It only says that the ordinary temporal notion of prior may fail. There may be deeper mathematical structures, non-classical states, Euclideanized regimes, bounce phases, pre-geometric foundations, or parent cosmologies from which our time emerges. What is threatened is not necessarily all notion of antecedents. What is threatened is the everyday form of antecedents we naively import into the problem. That distinction is subtle but crucial. There are at least three possibilities people often confuse. 1. Time literally begins, and there is no meaningful earlier physical state. 2. Classical time begins, but some more fundamental structure exists from which temporal order emerges. 3. Our universe is preceded by a prior physical phase, but a before has to be redefined using non-classical or model-dependent language. These possibilities feel different, and modern cosmology has not settled decisively among them. But what all of them teach us is the same philosophical lesson: the obvious, human picture of earlier and later may be the wrong map near the origin. That is the terrifying part. Not that we found a simple answer we dislike. That the question itself changes shape under pressure. And now we can understand why some physicists sought a more radical reimagining of the beginning, not as a sharp edge inside ordinary time, but as something smoother, more geometric, less like a first instant and more like a place where the concept of temporal edge dissolves. This brings us to one of the most elegant and disturbing ideas in 20th-century cosmology. The no-boundary proposal. Suppose the problem is not that the beginning is hidden. Suppose the problem is that we keep imagining it as an edge. Stephen Hawking, together with James Hartle, proposed one of the most famous attempts to rethink the beginning along exactly these lines. The no-boundary proposal, stated very roughly, suggests that if we describe the very early universe using a certain quantum gravitational framework, the distinction between time and space may change in such a way that the universe has no sharp temporal boundary in the ordinary sense. This is not an easy idea, and popular explanations often damage it. So let us move carefully. In some mathematical treatments, one can consider a change in the character of the metric so that what we ordinarily call time behaves more like a spatial direction near the beginning. In that regime, the universe can be pictured not as emerging from a singular edge but as having a smooth, rounded geometry. The classic metaphor is the surface of the Earth. The North Pole is a special place, but it is not a cliff. You do not fall off the top of the globe. The geometry closes smoothly. Hawking's point, in popular form, was that the universe might begin in an analogous way, finite but without a sharp boundary demanding an earlier temporal region. If this picture is even approximately right, then asking what happened before the beginning would be like asking what lies north of the North Pole. Again, not hidden information, but misapplied direction. The no-boundary proposal is not established fact. It is an interpretation and a model within quantum cosmology, and its precise status remains debated. It is not the answer to the origin question. But its importance goes far beyond whether the exact formalism wins. It teaches a conceptual lesson that may survive even if the proposal itself is modified or replaced. The beginning of the universe may not be a point where time suddenly clicks on like a stopwatch. It may be a region where the distinction between time and non-time changes character so profoundly that the demand for a before loses its footing. There is something deeply unsettling and strangely beautiful in that. Human beings expect edges. We expect first moments to sit at the lip of a void. But no boundary thinking suggests the beginning might be more like a rounded cap of possibility, a place where the geometry of reality smooths off in a way that dissolves the need for an earlier temporal region. That is not the same as saying the universe came from nothing. Not the same as saying there is no mystery. Not the same as saying time is unreal. It is saying something subtler: the universe may not have a temporal edge of the kind our minds keep demanding. For many people, this is emotionally unsatisfying. It feels like losing the moment of origin rather than explaining it. But perhaps that reaction is itself revealing. We want an edge because edges feel narratable. The no-boundary picture asks whether the universe is obligated to provide a narratively satisfying beginning. Perhaps it is not. Perhaps the oldest human instinct, to demand a first door with a room behind it, is the very instinct the cosmos refuses to reward. Still, no-boundary models are only one attempt among many. Their deeper importance is that they push us into a more general realization: near the beginning, classical time may dissolve as a useful category. To understand why, we need to move further into the strange country where quantum cosmology begins. Quantum cosmology is the attempt to apply quantum principles to the universe as a whole, especially near regimes where classical spacetime ceases to be reliable. That sentence may sound straightforward. It is not. Quantum theory was originally developed to describe systems within the universe: atoms, particles, fields, interactions. Cosmology asks us to describe the universe itself, including the very framework of space and time in which ordinary physical systems are located. When those two ambitions meet, familiar concepts start to break. One of the strangest outcomes is that time, in some formulations, no longer appears in the fundamental equation in the ordinary way at all. The Wheeler-DeWitt equation is the most famous example. In oversimplified language, it is sometimes described as the equation in which the universe's wave function appears timeless. There is no external time parameter playing the role it does in ordinary quantum mechanics. This has led to one of the most provocative claims in theoretical physics: perhaps time is not fundamental, but emergent. That statement must be handled with enormous care. It does not mean clocks stop. It does not mean change is an illusion in the trivial sense. It does not mean physicists have proven our experience of flow is fake. What it means is that at the deepest level of formal description, the variable we call time may not be basic. Instead, temporal order may arise from relationships between physical degrees of freedom, from change, correlation, decoherence, semi-classical approximations, or coarse-grained structure. This is difficult because the human mind instinctively imagines time as the thing inside which change occurs. Quantum cosmology tempts us toward the inverse thought: perhaps what we call time is a way of organizing change once certain structures become classical enough to support that description. In that picture, asking what happened before time becomes even more unstable. You are no longer asking what happened before a master parameter started. You are asking whether the deeper quantum state of the universe admits something that later, under special conditions, gets interpreted as time at all. The metaphysical disorientation here is severe. We may be asking for a before in a regime where before has no stable meaning. That line is not a metaphor. It may be a physically accurate warning. Near the beginning, if spacetime is subject to quantum uncertainty or replaced by more fundamental structures, the crisp distinction between a sequence of moments may blur. Classical trajectories may give way to amplitudes. Smooth geometry may become approximate. The difference between possible histories and actual history may not be separable in the ways ordinary language demands. This does not mean anything goes. It means the origin regime may require a kind of explanation that no longer resembles the storytelling habits we inherited from middle-sized reality. And that in turn explains why origin cosmology is so philosophically combustible. It invites people to fill the gaps with metaphysics. But the real lesson is more disciplined and more disturbing. The universe may not be failing to tell us what happened before. It may be telling us that what counts as happened changes near the beginning. There is another way to put this. Classical time may be a late achievement of the universe, not an eternal backdrop. If so, then the earliest regime is not merely early in time. It is prior to time in a more structural sense, not necessarily temporally prior, but prior in the hierarchy of description. The world may have had to become the sort of thing that supports time as we know it. This does not end the origin problem. It transforms it. Instead of asking what event happened before the first event, we ask under what conditions a temporal description emerges from a deeper non-classical state. That is a very different question. It may also be the more meaningful one. Still, not all cosmologists are satisfied with timeless approaches. Some prefer models in which our universe emerged from a prior phase, not necessarily in ordinary time, but in a physically describable process with its own antecedent structure. And this is where one of the most famous ideas in modern cosmology enters the story. Inflation. Inflation is one of the most influential ideas in cosmology because it does two things at once. It solves problems. And it creates new ones. The basic idea is that the early universe underwent a brief period of extremely rapid exponential expansion. This helps explain several otherwise puzzling features of the cosmos: why the universe appears so spatially flat, why widely separated regions have nearly the same temperature, and how tiny quantum fluctuations could be stretched into the seeds of large-scale cosmic structure. These are not minor accomplishments. Inflation became central because it made the observable universe easier to understand. But what does it do to the question of what existed before time began? The answer is complicated. Inflation does not straightforwardly solve the ultimate origin problem. In many versions, it describes a phase of the early universe, an extraordinary one, yes, but still a phase. It can explain how our observable patch came to look the way it does. It does not necessarily explain why there was an inflating state in the first place, what preceded it, or whether inflation itself is past eternal. This is where inflation becomes philosophically dangerous. It feels like an origin story because it reaches so deep into early cosmic history. But often it relocates the question rather than erasing it. We learn how one set of initial conditions might evolve into the universe we observe, only to find ourselves asking why those conditions were there at all. In other words, inflation may answer part of the how, while leaving the deepest why suspended. That is not a criticism. It is how science often progresses. We break a large problem into tractable ones. But culturally, inflation is sometimes treated as if it removed the mystery of beginnings altogether. It did not. There is another subtlety. Inflation is strongly motivated and widely influential, but the underlying mechanism, the exact field or fields responsible, the detailed potential, the relation to deeper high-energy physics, remains an active area of research. We have evidence consistent with inflationary predictions, but not a complete final theory of inflation's fundamental origin. And once again, that means the door behind the door remains tempting. What set inflation off? Was it eternal into the past? Did it emerge from a quantum tunneling event? Did it begin from a no-boundary condition? Was it itself born from a bounce? Each option carries its own metaphysical weather. The emotional power of inflation lies partly in its fertility. It shows that the early universe may have contained phases of extraordinary dynamical transformation beyond what naive Big Bang pictures imagined. The terrifying part is that such fertility can make the origin feel less like a clean first moment and more like a branching, layered, or perhaps generative structure whose beginning is even harder to locate than before. If inflation is part of the story, the question, before time began, may become, before which time? The clock relevant to our hot Big Bang phase may not be the deepest clock in the architecture. Or there may be no deepest classical clock at all. This is where cosmology becomes almost too productive for its own good. Every time a model explains the visible universe more elegantly, it risks generating a larger metaquestion outside the frame. Inflation solves. Inflation delays. Inflation relocates. Inflation magnifies. And for some versions of inflation, the relocation becomes so vast that the universe we inhabit may be only one local region in a much larger process with no obvious end. Which brings us to one of the most intoxicating and dangerous ideas in modern cosmology. Eternal inflation. If inflation happened once, it already makes the early universe stranger. If inflation happens eternally in parts of spacetime, it can make reality feel almost impossible to hold in one mind. The idea of eternal inflation arises in some inflationary models where the inflating state does not end everywhere at once. Instead, inflation continues in some regions while locally ending in others, producing bubble-like pocket universes or cosmological domains with potentially different histories and, in some frameworks, different low-energy physical properties. Our observable universe, on this view, could be one bubble among many. Immediately we must slow down. This is not established fact. It is not directly observed. It is not proven by inflation, in some simple way. It is a serious theoretical possibility emerging from certain inflationary frameworks, and it has been taken seriously by many cosmologists. But it remains speculative, especially regarding testability and measure problems. That said, even as a speculative frontier idea, eternal inflation matters deeply for our question. Because if our universe is a local pocket within a much larger inflationary structure, then the phrase, "before time began," becomes radically ambiguous. The local time of our hot Big Bang phase may begin at bubble nucleation or reheating, while the larger inflationary background possesses its own structure, perhaps not a single global time in any ordinary sense. In that scenario, there may indeed be something before our local cosmic history, but not before time in the absolute sense. What came before might be apparent inflating spacetime or some deeper quantum state from which bubbles form. This is why the multiverse debate is so dangerous for the imagination. It offers the mind exactly what the mind craves, another room behind the door. But it also makes the architecture so enormous, so fragmented, and so difficult to observationally constrain that explanation itself starts to fray. Instead of one beginning, we get a fertility of beginnings. Instead of one time, perhaps layers of temporal structure. Instead of solving the origin problem, we may merely relocate our ignorance to a larger scale. There is a haunting possibility here. The human mind wants a first room. Eternal inflation offers a hotel without a clear lobby. That is not nothing. It is not simplicity. It may not even be explanation in the emotionally satisfying sense. Worse, eternal inflation comes with deep conceptual problems of its own. If inflation produces endless pocket universes, how do we assign probabilities? What counts as a typical observer? How do we define measures on infinite ensembles? How do we extract testable predictions from a process that may generate almost everything permitted? These are not side issues. They strike at whether the framework remains scientifically manageable or drifts toward anthropic storytelling. Still, the appeal endures because eternal inflation appears to give the origin problem another dimension. The beginning of our universe may not be the beginning of all physical structure. But even then, we have not answered the deepest question. We have only learned that before may refer to another level in a hierarchy rather than to absolute non-being yielding to being. The ancient instinct for an earlier cause is not extinguished. It is given a more elaborate maze. And for some cosmologists, that maze is still too much like a sideways evasion. They seek a more concrete possibility. Maybe our universe was not born from an eternally inflating background, but from a previous cosmic phase. A contraction. A prior universe. A bounce. So now we move to one of the most intuitively appealing families of origin ideas. Not a first beginning. A rebound. Among all the attempts to imagine what came before the Big Bang, bounce models may be the easiest for intuition to love. Instead of a universe emerging from an absolute first instant, imagine a prior phase. Perhaps a contracting universe that reaches extreme density and then rebounds into expansion. Perhaps a cyclic cosmos passing through repeated phases. Perhaps our Big Bang was not the beginning of everything, but the transition point between an earlier state and our current one. Immediately the old human instinct feels relief. There is another room behind the door after all. Bounce and cyclic cosmologies have appeared in multiple forms across the history of physics and philosophy. Some are simple and largely obsolete. Others are sophisticated modern constructions tied to quantum gravity, scalar fields, brain-world scenarios, or modifications of classical relativity. Their appeal is obvious. They avoid a singular one-way origin. They replace the terrifying finality of the beginning with continuity. They let us preserve a kind of antecedence, something came before, though not necessarily in the everyday sense. But these models must be handled carefully. Not all bounce ideas are equally serious, and none have become the uncontested standard picture. They face significant technical challenges, avoiding uncontrolled anisotropies, explaining entropy growth across cycles, maintaining stability, matching observational constraints, and producing a bounce without pathologies. Some cyclic models solve one problem while generating another. Still, they matter because they reveal a legitimate physical possibility. The Big Bang may not be the first event, but the first event in our expanding phase. That is a conceptually enormous shift. The beginning of our cosmic history would not be the beginning of all structure, merely the beginning of the chapter accessible to us. But even here, the word before requires discipline. If a bounce occurs, then yes, there may be a prior phase in some physically meaningful sense. Yet whether the temporal relation across the bounce is smooth, emergent, or fundamentally reinterpreted depends on the model. Some versions preserve an ordinary causal order more readily than others. Some rely on quantum gravity corrections that alter the structure of spacetime near the bounce itself. In other words, the bounce gives back an earlier room, but often in a building where the architecture has changed. There is also a deeper philosophical issue. Bounce models are attractive partly because they satisfy the mind's dislike of absolute beginnings. But nature is not required to satisfy that dislike. The merit of a bounce model must come from its physics, not its emotional comfort. We should be suspicious whenever a cosmological idea becomes popular partly because it rescues intuition. Even so, the bounce remains one of the most serious ways physics has tried to make before physically meaningful again. Instead of asking what happened before time began, we ask whether our observed temporal order emerged from a previous phase of spacetime or proto-spacetime that underwent a transition. And that brings us to one of the most technically interesting frameworks for such a possibility. Loop quantum cosmology. Time we know. Notice how recurring the theme has become. Again and again, the theories that try to go deeper do not simply supply one more earlier event. They alter what an earlier event could even mean. The hallway may continue. But not with the same architecture. There is also an emotional lesson in loop quantum cosmology. It reminds us that singularities are not sacred. They may be artifacts of classical description, much as the ultraviolet catastrophe was an artifact of classical reasoning before quantum theory intervened. The beginning might not be a literal puncture in explanation. It may be a place where our old explanatory language folds and a new one takes over. That possibility should both comfort and unsettle us. Comfort, because it means the universe may remain intelligible deeper than classical relativity suggests. Unsettle, because that deeper intelligibility may be alien to human common sense. And now we arrive at a word that quietly poisons almost every public discussion of cosmic origins. Nothing. Few words do more damage in cosmology than nothing. People say the universe came from nothing. They say there was nothing before the Big Bang. They ask why there is something rather than nothing. They imagine an empty blackness before creation. They picture a sterile void waiting to be interrupted. But in serious physics, these images are almost always misleading. Nothing, in ordinary language, means absence. No objects. No matter. No space. No time. No fields. No laws. No structure. Absolute non-being. Physics almost never deals directly with that kind of nothing. When physicists speak loosely of a vacuum, they do not usually mean philosophical nothingness. They mean a lowest energy state of fields. But fields are already something. Laws are already something. A quantum vacuum is dynamic, structured, and governed. It can contain fluctuations, expectation values, geometry, and the possibility of particle excitations under the right conditions. Calling that nothing may be rhetorically tempting, but it is conceptually dangerous. Likewise, when cosmologists say the Big Bang was not an explosion into empty space, they are not saying the universe emerged from a literal void in the metaphysical sense. They are saying the framework of space and time itself may be part of what is at issue. The origin problem is not solved by smuggling in an empty stage and calling it nothing. This matters for our title more than almost anything else. What existed before time began tempts the imagination toward a dark blank. But a blank is already a kind of scene. It is visualizable. It feels like a room with the lights off. That is not non-being. It is merely a very sparse something. The universe may not grant us even that. Or it may grant us underlying structures so abstract that the word nothing becomes useless. A quantum state. A pregeometric network. A path integral over compact geometries. An inflating background. A prior contracting branch. A timeless wave function. None of these are nothing. They are different kinds of theoretical somethings. This is one of the most valuable acts of discipline in origin cosmology, refusing to let the word nothing do emotional work it cannot do scientifically. There is a second danger too. Once the public hears, the universe came from nothing, people either celebrate the phrase as ultimate explanation or reject it as absurd. Both reactions are premature, because the phrase usually compresses several distinct claims into one slogan. Did space arise from a prior non-spatial theory? Did classical time emerge from a non-classical structure? Did our observable universe tunnel from a quantum state? Did a vacuum fluctuation occur in a larger background? Did a bounce replace a singular beginning? These are very different possibilities. None is captured honestly by the word nothing. The terrifying truth may be that the origin of the universe is not a contest between something and nothing as ordinary language imagines them. It may be a contest between different layers of structure, different meanings of existence, and different regimes in which words like before, cause, and void no longer line up cleanly. There is something almost humiliating in this. Human language evolved for middle-scale reality. We name rocks, storms, births, deaths, paths, containers. Then we drag those words to the edge of cosmology and ask them to carry impossible weight. Sometimes they do. Often they break. Nothing is one of the words that breaks first. And when it breaks, another cherished concept becomes unstable with it. Causality. Because if the beginning is not simply an event in time, then cause itself becomes slippery near the origin. Cause and effect are the backbone of intelligibility. We feel this so deeply that explanation itself often seems synonymous with causal ancestry. To explain something is to trace it to what brought it about. So when we ask what existed before time began, we are often really asking a causal question in disguise. What caused the universe? That question sounds decisive. It may also be treacherous. Causality, as ordinarily understood, is a temporal relation. Causes precede effects. One thing happens, then another follows from it. But if time itself is part of what emerges with the universe, then the familiar machinery of causation may not apply in the straightforward way we expect. We may be trying to use a tool outside the domain in which the tool is defined. This is one reason some philosophers and physicists warn that asking for the cause of the universe may involve category confusion. If causation is a structure within spacetime, then asking what caused spacetime as a whole may be like asking what physical location contains all locations. The concept strains against its frame. And yet cosmology does not simply abandon causality. It refines it. Some origin models preserve meaningful antecedent structure. Bounce models, for example, can provide a prior phase whose dynamics lead into ours. Eternal inflation offers parent processes. Quantum tunneling proposals suggest transitions from one state to another. In these contexts, there may be law-like generative relations even if the ordinary picture of linear cause and effect becomes complicated. So the problem is not that causality vanishes. The problem is that causality near the beginning may not be the familiar, everyday causality of billiard balls and lightning strikes. There are at least 3 levels here. First, causal explanation within the universe. Stars form from collapsing gas, planets form in disks, galaxies merge, black holes grow. This is familiar science. Second, cosmological explanation of our early state, inflationary dynamics, quantum fluctuations, reheating, symmetry breaking, nucleosynthesis. Still scientific, though more extreme. Third, metacausal or generative explanation of the framework itself, why there is a universe, why these laws, whether our spacetime emerges from a deeper structure. Here causality becomes philosophically unstable because the usual temporal scaffolding may be missing or emergent. This is where many discussions go wrong. People either demand ordinary causal language at the deepest level or forbid all meaningful explanation beyond the observable universe. Both extremes are too simple. The truth is that origin cosmology lives in a borderland where some explanatory relations survive, but not always in the form ordinary intuition demands. The universe may have to be explained without the explanatory grammar we evolved to trust. That is a frightening possibility. Not because explanation disappears, but because explanation may become less like narrative sequence and more like structural necessity, boundary condition, transition amplitude, or mathematical consistency. We want a first domino. Physics may offer a self-consistent geometry, a quantum state, a bounce law, or a timeless relation from which classical sequence later emerges. That feels cold to the human mind. It feels less like a story and more like architecture. But perhaps that is exactly the point. We keep expecting the universe to answer us in the form of a story because stories are how minds remember causes. The cosmos may answer in the form of structure. And now we must pause and clean the ground beneath us. Because by this point in the documentary, the line between well-supported science, mainstream interpretation, and speculation could easily blur if we do not redraw it with care. This is the section where wonder must become precise. Not to reduce mystery. To protect it from distortion. #### What is established? It is strongly established that the universe has expanded from a hot, dense early state. The evidence for this is overwhelming: cosmic expansion, the cosmic microwave background, and light element abundances all converge on this picture. It is also established that general relativity treats spacetime as dynamical rather than as a passive stage. Space and time are not fixed containers in the modern classical picture. They are part of the physical structure being described. It is further established that classical extrapolation toward the earliest times leads to singular behavior, signaling that classical general relativity alone is not expected to be sufficient all the way to the beginning. It is also established that quantum effects become relevant in extreme regimes and that a complete account of the earliest universe almost certainly requires quantum gravity or some comparably deep framework. These points are robust. #### What is mainstream interpretation? It is mainstream to say the Big Bang was not an explosion into pre-existing emptiness. It is mainstream to say that in classical cosmology, talking about a simple before may be problematic because time itself is bound up with the spacetime description of the universe. It is mainstream to regard singularities not as comfortable final answers but as signs that our present theories reach their limit. It is also widely accepted that ordinary intuition about time and causality may not survive unchanged near the origin. These claims are not fringe. They are part of how responsible cosmologists frame the problem. #### What is serious but unsettled? Inflation is widely used and strongly motivated, but the exact fundamental story behind it remains unsettled. The no-boundary proposal is influential and elegant, but not established fact. Quantum cosmology offers powerful conceptual tools, but no single timeless formulation has become universally accepted as the final picture. Bounce models, cyclic universes, and loop quantum cosmology are serious research directions, but none has become definitive. Eternal inflation and multiverse ideas are taken seriously by many experts, but they remain speculative and face testability and measure problems. These are legitimate scientific frontier ideas. They deserve interest, not certainty. ###. What is overreach? The claim that science has proven what existed before time began. The claim that the universe definitely came from literal philosophical nothing. The claim that one speculative model has solved the origin problem. The claim that because before may be problematic, the question is meaningless in every possible sense. The claim that cosmology has disproven causality, metaphysics, or explanation altogether. These are examples of turning the frontier into theater. The actual situation is harder and more beautiful. Physics has not proven a final account of what existed before time began. It has done something more unsettling. It has shown that the obvious version of the question is less stable than we thought, while several deeper versions remain scientifically fertile. That is a much more interesting result than certainty would have been. And it leads to one last level of the problem. Not physics this time. Psychology. Why do our minds resist a beginning that has no before? There is a reason the origin question never stays purely technical. It attacks a nerve in human cognition. We are creatures who orient ourselves through continuity. We do not merely like explanation. We need it in a particular form. We want a chain. One event leads to another. One room leads to another. One sentence continues from a previous sentence. Even when a story starts in the middle, we trust that a deeper earlier frame exists somewhere behind it. A beginning without a before feels, to the human mind, almost offensive. It feels like being denied the right kind of answer. That emotional resistance is not a failure of intelligence. It is a side effect of how embodied minds evolved. We live in a world where local causation works, where continuity is powerful, and where sudden absolute starts are rare or non-existent in ordinary experience. So our deepest explanatory habits are shaped by contexts in which every beginning is embedded in a prior environment. The universe as a whole may be the first thing we have ever tried to understand that does not owe us that embedding. That is almost impossible to feel cleanly. People can repeat the sentence, "Time may begin with the universe," and still secretly picture some silent waiting room behind it. They imagine a black nothingness. Or a prior clock. Or a divine interval. Or a metaphysical buffer. The mind keeps trying to reinstall background because background is how explanation normally works. This is why cosmology and theology keep brushing against one another even when they mean different things. The psychological demand for a before is so strong that if physics withholds it, imagination rushes in to supply one. But imagination supplies it in familiar human forms: a creator, a womb, a prior realm, a void, a cyclic recurrence, a hidden domain. These may be profound ideas, but they also reveal how difficult it is for the mind to tolerate a beginning that is not a local event in a larger stage. There is another discomfort too. A beginning without a before threatens our sense of causality's authority. If there is no earlier temporal region in the ordinary sense, then explanation may have to become less narrative. It may depend on consistency, geometry, quantum state, or law rather than on a familiar sequence. That feels less satisfying not because it is worse science, but because it offers less psychological grip. We prefer an earlier cause because an earlier cause feels like understanding. The universe may be telling us that some kinds of understanding are not ancestral but structural. That is a hard lesson. The oldest human instinct is to demand an earlier room behind every door. Physics may be telling us the hallway itself begins here. No wonder the mind resists. And perhaps this is why origin cosmology can feel almost spiritual without ceasing to be scientific. It forces us to confront not only what the universe is like, but what kind of explanatory animal we are. We bring stories to the edge of spacetime and discover that some of them no longer fit through the opening. That discovery can produce panic. Or humility. Or awe. Maybe all three. Because what cosmology is teaching us is not simply that the universe is difficult. It is that the deepest levels of reality may not have been shaped for intuitive access by minds evolved on one wet planet around one ordinary star. That does not make the universe hostile. It makes it other. And now, after all of that, we can finally say as clearly as possible what the terrifying truth is. Not what definitely existed before time began. But what physics has forced us to understand about the question itself. Let us gather the pieces without pretending they fit comfortably. We began with a question that feels almost impossible not to ask. What existed before time began? And the first shock of modern cosmology is that this question may not survive intact all the way to the depth at which it is aimed. The Big Bang, properly understood, is not an explosion into an earlier emptiness. It is the hot, dense early state of an expanding universe whose spacetime structure is itself part of the story. General relativity makes space and time dynamical. Classical extrapolation leads toward singular behavior, but singularities are warning lights, not comfortable metaphysical trophies. Near the beginning, classical physics stops speaking clearly, and quantum gravity becomes unavoidable. From there, the picture fractures into possibilities. Maybe the universe has no sharp temporal boundary in the naive sense, as in no boundary proposals where the distinction between time and space changes character near the origin. Maybe classical time dissolves into a deeper quantum description in which temporality is emergent rather than fundamental. Maybe inflation explains our observable patch while relocating the deeper origin problem elsewhere. Maybe eternal inflation makes our universe one local chapter in a much larger process. Maybe a bounce replaced the singularity. Maybe a prior contracting phase preceded our expansion. Maybe loop quantum cosmology is hinting that the universe rebounds where classical relativity would have broken. None of these ideas has been proven as the final answer. But together they have done something extraordinary. They have made the ordinary version of the question far stranger than human intuition expected. What existed before time began? The deepest honest answer may be. Perhaps that depends on what you mean by time, by existed, and by before. That is not evasion. It is the hard-earned result of physics colliding with the limits of ordinary language. We may be asking for a before in a region where before has no stable meaning. We may be trying to tell a story in a place where structure matters more than sequence. We may be demanding a temporal ancestor for a framework in which temporality itself is an emergent achievement. The beginning may not be a moment inside time. It may be the place where time becomes possible. That line is not final truth. It is a frontier warning. But it may be the most important sentence in the entire problem. Because if it is even partly right, then the universe has done something more radical than beginning. It has generated the conditions under which beginning and before and after become meaningful categories at all. The origin is not merely an event to be dated. It may be the threshold at which the grammar of events first becomes available. This is what makes the question so terrifying and so beautiful. We came looking for one more room behind the first door. Physics may be telling us that the first door is not embedded in a hallway the way all our ordinary doors are. The hallway itself may begin here. And yet the mystery has not been killed. On the contrary, it has deepened. Physics has not proven what existed before time began. It has not shown that there was definitely nothing. It has not sealed the case for bounces, for no boundary, for eternal inflation, or for timeless quantum states. What it has done is more unsettling than certainty. It has shown us that reality near the origin may not fit the forms of explanation we trust most. Time may be less fundamental than experience suggests. Causality may become slippery near the beginning. Backgrounds may fail. Boundaries may smooth out. And the oldest human habit, to search for the earlier cause behind every visible thing, may encounter, for the first time, a domain where the demand itself becomes unstable. This does not make the universe meaningless. If anything, it makes it more severe, more elegant, and more worthy of awe. Because it means the cosmos is not merely bigger than we thought. It is conceptually less obedient. It does not owe our minds a first clock waiting in the dark. It does not owe our language a clear outside. It does not owe our narratives an earlier room. There may be one. There may be something deeper. There may be structures, phases, or foundations beyond classical time. But if there are, they may not resemble the simple before that the human heart keeps asking for. That is the haunting end of the story. Not that we found what was before time. That we discovered why the question opens onto a place where ordinary temporal intuition may stop being reliable. The universe may not be hiding a secret moment before the first moment. It may be hiding a deeper truth. That the framework in which moments make sense is itself part of what had to come into being. And if that is true, then the terrifying truth about what existed before time began is not that physics has an answer we cannot bear. It is that physics has shown us why the question itself may be stranger than the mind that asks it. The oldest human instinct is to demand an earlier room behind every door. But the universe has begun to whisper back, with increasing precision and increasing coldness. There may be no earlier room. There may only be the threshold where rooms, doors, hallways, and the very idea of earlier first become possible. And from inside time, that may be the strangest truth we will ever hear.